So, yeah, I'm telling you this many times. So a relation R from X to Y is a set of pairs X comma Y, where X is in A, X, Y is in Y. Some just collection of pairs, any collection of pairs X comma Y will be a relation. So in other words, it's just a subset of X cross Y. All right. So for example, R is a relation from, say, X 1, 2, 3, 4, and Y A, B, C, D. Like this. I'm just collecting some of them, some of the pairs, like this. 2, C, 4, D. Any collection would be a relation. All right? I want this to be B. Okay, so relation, just collection of pairs. But here, matrix of relation means we are going to represent a relation using a matrix. We represent R as a matrix. So, as follows. So X, the labels of the rows will be the elements in X. So it's 1, 2, 3, and 4. Labels of the columns will be the elements of Y, A, B, C, D. And whenever there is element X comma Y, then fill the entry X comma Y entry with 1. For instance, 1 comma A, so 1 comma A, so row 1, column A. Find that entry and then fill it with 1 for this, okay? And 1 comma D, so 1 comma D, so fill it with 1. 2 comma C, fill it with 1. 4 comma B, fill it with 1. 4 comma D, fill that entry with 1. What about the remaining ones? Remaining entries? They will be 0. They will have zeros. Fill the remaining entries with zeros, like that. This is called the matrix of relation. But of course, it depends on the matrix will change if you reorder the elements here. So it's fine. You can have either like 2, 1, 4, 3, B, C, A, D. I don't know, just B, C, D, A. Any order will be fine. The matrix will, of course, will change. So for instance, here 1 comma A, 1 comma A. Now we have here 1 comma D, 2 comma C, 4 comma B, 4 comma D, like that. And then fill the remaining entries with zeros. This is the matrix of the relation with respect to this order and with respect to this order. So we have to decide which order of the elements we use. All right. So let me write down the precise definition in the next page. So definition. R is a relation from X to Y. The matrix of R here relative to ordering of X and Y. So we assume that we are given some certain ordering because we want to order the rows and columns accordingly. is okay, let's say the ordering is given like this: x1 dot 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 xn. Here y1 dot 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 ym. Say so. It's going to be n by m matrix. M, which I denote a, whose ij entry is like this. So here ij is from n by m entry, m matrices, where aij is either 1 or 0. 1 if xi yj is in the relation, and otherwise, like we just defined in the previous example. You fill the entry with 1 if there is a relation, and 0 otherwise. So we assume that the order is given. For example, R is relation from 2, 3, 4 to 5, 6, 7, 8, say. So the order we are using just this order, 2, 3, 4, this. If I don't say anything, just assume that the order is like the order of the elements written there. Now what is the matrix M? By the way, I didn't define R yet. X, R, Y. So basically this is another notation for this. Sometimes we write X, R, Y. This is exactly the same thing. Same notation. Like sometimes, because we write relation in between. So yeah, this is the same thing as this. The definition is X divides Y. So what is the matrix of the relation? So we have 2, 3, 4 rows labeled by 2, 3, 4, columns, 4 columns labeled by 5, 6, 7, 8. And then we fill each entry 1 if there is a relation, 0 otherwise. 2, does 2 divide 5? No, so this will be 0. 2 divides 6, so it's yes. 2 does not divide 7. 2 divides 8. 3 does not divide 5. 3 divides 6. No. Does not divide these, but divides 8. So this is the relation, matrix of the relation R. Any question? You would have this question: why are we doing this? Right? You should ask this kind of question. What's the good thing about this representation? You can say one thing. One thing is, yeah, it's kind of a compact way to write your relation. Right? If you look at this, you can see whether two are related or not quite easily. That's one thing. But there is something better, some better reason for this. There is a very nice property of this matrix of relation. It is very useful when we compute the composition of two relations, right? Matrix of relations. These are useful when computing R2, R1. So do you remember what this is? The composition of two relations. It's like composition of functions. So this is, of course, we have to assume that R1 is from, it's a relation from X to Y, R2 is a relation from Y to Z, then R2 compose R1 is a relation. Oh yeah, this should be not an element but a subset, right? Subset, subset, subset. And this is going to be a relation from X to Z defined as follows. X comma Z, where Z, where there is Y in Y, satisfying this X comma Y in X, X no, in R, the first relation, Y comma Z in R2. This is the definition of the composition of two matrices, two relations. Like it's like composition of functions. The theorem is, in this situation, let's say A1 is the matrix of relation of relation R, a matrix of R1, A2, matrix of R2. And of course, we assume that the ordering of X, Y, Z are given. Then, what is the matrix of R2, R, I don't know, R2 compose R1 is almost like this, is A1 times A2. It's a matrix multiplication, not quite the same. It's like almost, not very precise. Let me be precise. Is the matrix. Okay. Or let me just write and explain again. Almost A1, A2. It's a multiplication of two matrices. Here, this means the following. So, what is the property? What is a very simple property of a matrix of relation? It is a 0-1 matrix. Entries are always zeros or ones, right? Every entry is either 1 or 0. So we are only interested in one non-zero elements, non-zero entries, because non-zero entries are all the entries with 1. This means non-zero entries of the matrix of this is exactly the non-zero entries of this. This is what I mean by they are almost the same. They're not exactly the same because this matrix may have integers greater than 1, like 2 or 3. But if you only look at non-zero entries, then they are exactly the same. The positions, I mean, the positions of non-zero entries. Positions of. Let me give you an example. I'm not going to prove this precisely, but I'm going to give you the idea why this should be true. An example, if you look at an example, you will understand why this must be true. And y, a comma b, z, x comma y comma z. So R1, I'm going to define R1 like this. Actually, we did this before using just the definition of the composition, but we are going to do this again using the matrices. B comma Z. So what is the relation for R1? We have like 1, 2, 3, A, B, right? So 1 comma A is here, 2 comma B is here, 3 comma A, 3 comma B, like that. And A2, what is A2? So now, the rows are labeled by AB, columns are labeled X, Y, Z, like that. A comma x, so here a comma x, a comma y, b comma y, b comma z, like that, and zeros elsewhere, like that. Now, if you compute R1 and R2, the composition of R1 and R2 like this, just by using the definition, we know this 1 comma a and a comma x, so we have 1 comma x, right, and 1 comma y. I'm going to write down this like this. 3 comma z. If you compute them, then you can see this. So what is the matrix for this? Matrix of this relation, R2 compose R1. So it's a relation from x to z, so we have 1, 2, 3 for the labels of the rows, and then x, y, z for the labels of the columns, right? So we have 1 comma x, so here is 1, 1 comma y, 2 comma y, 2 comma z, 3 comma x, y, z. So it's like that. 0, 1 matrix, of course. Now let's compute A1 times A2. What is A1 times A2? It's going to be 3 by 3 matrix. So we for the 1 comma 1 entry, we multiply these two, this row and this column. Take a dot product if you want. This times this plus this times this, which is 1. And this, again 1. This and this, 0. And this what? 0. 0 plus 0. And this is 1. This and this is 1, right? And this is 1. And now here, 1 times 1 plus 1 times 1, which is 2. And this is going to be 1. They are different, but they are non-zero. Their positions, the positions of zeros or the positions of non-zero elements are the same, right? So here you can obtain this by replacing every non-zero entry by 1. If it's 1, just leave it there. If it's greater than 1, replace it by 1, like this. 2 is replaced by 1. So that everything is now zeros and ones. Then the theorem, what the theorem says is that this is exactly the matrix of the composition. R2 compose R1. Do you see why? The secret is okay. Let me illustrate how this works. Okay. Okay. The setting here is that R1 is a relation from x to y. R2 is a relation from y to z. Then R2 compose R1 is a relation from x to z. This is what you know. And what does this mean? X comma z is in R2, R1. This means what? There is something y where xy is in R1, and at the same time yz in R2, right? What does this have to do with matrix multiplication? Think about the matrix. The A matrix here, A1 and A2. Think about A1 and A2. So here we have like x1, x2, something like that, right? Here we have y1, something like that. Here the rows are labeled by y. So xn, y, ym, say, ym. Here z1, z, ls, for instance. Now we are interested in, so what is the entry here? What is the xy entry? Here, let's say xi and xz, right? This entry, how do you obtain this entry when you multiply two matrices? Here we have x, this row. Here we have this column, z. And then you multiply this and this, this and this, and this and this, etc. Now, suppose that this is 0. What does that mean? No matter which position you are looking, like ith position here, let's look at this ith position and ith position here. Either this is 0 or this is 0 for every I. That's the only case when we obtain 0. Otherwise, if both are non-zero, that means we have 1, 1, because what's this? Because they are 0, 1 matrices. If there is 1, 1, then we get something bigger than 0, right? It could be 1, or it could be 2, or etc., but it is bigger than 1. But this means there is some y. This means this is y, and this is y, yi precisely. That means x comma y is in R1, y comma z is in R2. So if this is greater than 0, if it's non-zero, in other words, there must be some y satisfying this. This is basically the idea, or this proof basically. So the matrix multiplication, if you follow this operation, then it tells us that if it's non-zero, there must be some y here. Is this okay? All right. And this composition is useful because this is a useful thing, because sometimes we consider a composition of two relations very often. We learned 4 important properties of conditions for relations: transitive, reflexive, antisymmetric, symmetric, and transitive. And especially transitive condition can be checked using matrices. So, for instance, let's say R is a matrix on X, A, B, C, D, A, comma A, B, comma B. Or not just transitive, all those properties can be checked very easily if you know the matrix of relation. Suppose, so this is given, this is a relation on X, A, B, C, D. So our question here is this reflexive, is this symmetric, antisymmetric, or transitive? That's what we want to know. Let's consider the matrix of the relation, A, B, C, D, A, B, C, D. A comma A, so here is 1, B comma B, C comma C, D comma D, A comma C, C comma P. I'm going to leave the remaining entries just there. If it's empty, it's 0. I'm not going to write zeros there. Let's compute A squared. So A squared means you just copy the same matrix and then try to compute A squared. What's that? So here, this times this. You know how to multiply two matrices, right? I'm going to write down the answer. If you compute the product, A squared, then it's going to be like this. Suppose that you know the matrix, and then because of this, you know how to compute this. Now, question is this reflexive? Is this symmetric? Is this anti-symmetric? Is this transitive? If you know A and A squared, it is quite simple. Is this reflexive, by the way? Suppose you are given a matrix. How can you determine whether the relation is reflexive or not? What's the definition of a relation? Reflexive relation. x comma x must be there for every x. X comma x is on a diagonal entry. So diagonal entry must be all ones, right? They are all ones in the diagonal entry, so it's yes, right? Diagonal entry is all one. If there is something 0 here, if there is only 1 0, if there is at least 1 0, then it's not going to be reflexive. Is this symmetric? What does symmetric mean in terms of matrix? The matrix should be symmetric matrix. Symmetric means if you take the transitive, it must be the same thing. But here, you have 1, but no 1 over here. So it's not symmetric, no. Okay? What about anti-symmetric? Is this anti-symmetric? What does this mean for a matrix? Anti-symmetric means x, y is in the relation, and both x, y, and x must be x equals y, right? Anti-symmetric condition is this. What does this mean in terms of matrix? You know, if x and y are different and both 1, 1 here, like this is the mirror image of this. If you have this, that's not going to be anti-symmetric, right? But here you cannot find those 1, 1, right? So it is anti-symmetric, yes. What about transitive? Yeah, this is this now we need a squared. Is this transitive? How can you see whether this is transitive or not? You compare non-zero entries of a squared and a1. Yes. Actually, there is a theorem or corollary of the previous theorem. We have a theorem over here, and the corollary is the following. Let me write down the corollary and then get back to this example again. The corollary is this. R relation on X. A is the matrix of R. Then R is transitive if and only if the following condition holds, the star condition. If star holds, if ij entry of a squared is non-zero, then ij entry of a is also non-zero, must be non-zero. If this condition holds, then R is transitive. What does this mean? R, this is non-zero. Oh, wait a second. Maybe oh yeah, that's right. This is correct. What does this mean? What does this mean, by the way? This a squared, so you multiply a squared is like that. And we get some entry here, ij, right? If this is non-zero, like something greater than 0, that means we have at least some non-zero entry here, and here, right? I say some k and I, j, right? We have 1 and 1 at the same position, right? This means, let's say this is x and this is y and this is y and this is z. This means x comma y is in relation R, y comma z is in relation R. So this is non-zero means there exists y, right? Satisfying this. Then x comma z must be in R. This is what the condition says. So this means this implies this. That's exactly what a transitive relation means. So if something is non-zero in A squared, it must be non-zero in A. Then that is transitive, okay? For every ij entry. So using this corollary, we can see whether it's transitive or not. Let's go back to here. Here, is this transitive now? Now that we know the corollary. Look at non-zero entry. Here, this is non-zero. And look at the same entry here. This is non-zero. This is okay. This is okay. This is okay. This is okay. But here, look at this. This is non-zero, right? But this is 0, right? That means it's not transitive. No. Because here, this means we have, especially this means we have A comma something and something comma B. This means A comma something and something comma B they are in our relation. But this means, however, A comma B is not in R. So it cannot be transitive. Okay? That's what it means. So it will be very useful if you know this corollary. Is this okay? So let me write down the thing. So summarize what I did. So A is a matrix of relation R. So R is a relation on X, right? As before. Then R is reflexive if and only if what? In terms of matrix A. I'm going to write down this as a diagram. I got just that diagonal entries must be 1. We don't care about non-diagonal entries. Diagonal entries must be all 1. That is if and only if condition. What about R is symmetric? Symmetric means A is symmetric. A is a symmetric matrix. Symmetric, asymmetric means A is symmetric means A is equal to A transpose. If you flip your matrix along the diagonal, it must be the same thing. What about R is antisymmetric? This means A does not have this. Have this. Diagonal, for non-diagonal entries, does not have this kind of pattern. They are just symmetric, like that. If you don't have this, that's fine. The same here is a mirror image of this. If there is at least one pair of ones like this, then it's not going to be antisymmetric. But you cannot find this, then it's symmetric. Antisymmetric, if there is no pattern like this. And finally, R is transitive if and only if what? This condition holds. Ij entry of A squared is non-zero, then Ij, let me write just like a proposition. Ij entry of A must be non-zero for all ij. For all ij, if that entry is non-zero in A squared, that entry, the same entry must be non-zero in A. So using the matrix of relation R, A or A squared, if you know, if you know A and A squared, you can determine whether the relation is symmetric. All of this, you can determine all of this quite easily. Okay? Any question? All right, now let's see just one more example about the transitivity, because here we just saw something that's not transitive. You can show that something is transitive using this. I'm going to do this next page. R A comma A, B comma B, C comma C, D comma D. The same, I think it's not the same. B comma C, C comma B. So the matrix of the relation is like 1 0 0 0 0 1 1 0 0 1 1 0 0 0 0 1, like that, right? And A squared, if you compute this 1 0 0 0 2 2 2 2 and 1 0 elsewhere, it's like that, right? It's easy. Is this transitive? Is this transitive? Yes. Look at every non-zero entry here, and then go back to see the same position in A. That's still non-zero, right? This, the non-zero, or in other words, the positions of zeros is exactly the same as the positions of zeros, right? Just remove all the non-zero entries. Just look at the zero things. Here is exactly this part and this part. It's the same. In this case, that means if you have every non-zero entry here, this still non-zero entry here. This yes. Non-zero, 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 non-zero. That's okay. Oh, by the way, this is not if and only if condition, I think. This is kind of a special case. All we need is just this. If something is non-zero here, then it is non-zero there. They don't have to be the zeros don't have to be the same. Oh, maybe we need some. So for instance, I just come up with this. Suppose that matrix is like 0, 1, 0, 0. So the relation, that means the relation is like, if you say A, B, A, B, relation is A comma B, right? What is A squared? 0. Is this transitive? Is R transitive? Is R transitive? There are zeros, the positions of zeros are different, but it is transitive. Why? Every non-zero entry, if you look at every non-zero entry and then go back over here, that is still non-zero. If that condition holds, then that's true. Here, there's nothing, there's no non-zero entry. There's nothing to check. That is always true then. So the condition holds is transitive, yes. Okay? So in this example is kind of special. They can be the same. Sometimes their positions are exactly the same. But even though the positions are not the same, it can be transitive. So actually, if you want the precise condition, if positions of this, if you write this as a set, we must have this. This is transitive means. Transitive means positions of zeros here are contained in here. Okay. Oh, maybe, yeah, I think the other way around. Sorry about that. Because we are looking at non-zero entries. Or in other words, positions of non-zero entry. This is exactly the conditions. That's what the conditions. Okay. Are there any questions?